Hello friends, welcome to Shri Digambar Institute of Technology, Dausa. Myself Reena Jarwal from Electronics and Communication Engineering Department. Today I discuss about the time domain specification for second order system. Let us start. First, we discuss the specification for second order system, that is, if the response up to the settling time is presented, that is known as transient response, and the response after the settling time is known as steady state response. So we can see that the time before the settling represented the transient response, and the response after the settling time represent the steady state response. In last class we discussed that in transient response it generally vary continuously time, and in steady state response it is fixed. So let us start the parameter of the second order system. So first parameter is delay time. So generally delay time is represented by TD, and it is always equals to 1 plus 0.7 del by omega n. It is the time that is required for the response to reach 50% of the final value in first attempt. Generally it is calculated by this formula. Del is also represented by zeta factor. So this is the delay time. Now rise time. The rise time is the time needed for the output to be equal to the input for the first time. So generally it is represented for the time response of second order control system by an expression, that is C of t is equals to 1 minus e raised to power minus zeta omega n t by root 1 minus zeta square sine omega n root 1 minus zeta square bracket t plus phi. So generally here zeta is sometimes also represented as del. Here the value of phi is equivalent to tan inverse root 1 minus zeta square by zeta. So next, let the response reaches to 100% of the desired value. So put the value of Ct equivalents to 1. So put the value of Ct is equivalents to 1 is equals to 1 minus e raised to power minus zeta omega nt by root 1 minus zeta square sine omega n root 1 minus zeta square t plus phi. Now it is rewritten as e raised to power minus del minus zeta omega n tr by root 1 minus zeta square sine brackets omega n root 1 minus zeta square t plus phi equivalents to 0. Now the value of e raised to power minus zeta omega n t is not equals to 0. So this equation is rewrite as sine omega n root 1 minus zeta square t plus phi is equivalent to 0. Next, it is also rewritten as sine omega n root 1 minus zeta square t plus phi is equals to sine n pi. Now the value of n put as 1. So after putting the value of n, it is equivalent to omega n root 1 minus zeta square t r plus phi is equivalent to phi. Here tr is represented the rising time. So tr is equivalent to pi minus phi by omega n root 1 minus zeta square. So after calculating this, we represent the tr as pi minus tan inverse root 1 minus zeta square by zeta upon omega n root 1 minus zeta square. So we can say that the rising time tr is the time that is needed for the output to be equivalent to the input for the first time. So this is the formula for rising time. Next, peak time. Generally, peak time is represented as Tp. The peak time is the time that is required for the response to reach the first peak of the time response. Peak point is always the highest point of the response. So, it is represented as C of t is equals to 1 minus e raised to power minus zeta omega nt by root 1 minus zeta square sin omega n root 1 minus zeta square plus t plus phi. Generally, we know that this equation is the time response of the second order system. For maximum peak time, dc of t by dt is equivalent to 0. So, now this equation is rewrite as this: dc of t by dt is equivalent to e raised to power zeta omega nt by root 1 minus zeta square cos brackets omega n root 1 minus zeta square t plus phi omega n root 1 minus zeta square plus sin omega n root 1 minus zeta square t plus phi zeta omega n by root 1 minus zeta square e raised to power zeta omega nt is equivalent to 0. Now this equation is considered as equation number 1. Next, since we know that e raised to power minus zeta omega nt is equivalent to 0, so equation can be rewritten as cos omega n root 1 minus zeta square t plus phi root 1 minus zeta square is equivalent to sin omega n root 1 minus zeta square t plus phi brackets zeta. Put the root 1 minus zeta square is equivalent to sin phi and zeta equivalent to cos phi. And put the values and create the equation. So the last equation is rewrite as this. So after putting the value, equation 2 is equivalent as cos omega n root 1 minus zeta square t plus phi sin phi is equivalent to sin brackets omega n root 1 minus zeta square t plus phi cos phi. Now after calculating this, sin omega n root 1 minus zeta square t plus phi by cos omega n root 1 minus zeta square t plus phi is equivalent to sin phi cos phi. That is this. Now after solving this, it is represented as tan omega n root 1 minus zeta square t plus phi is equivalent to n pi. So the time that is varies for peak value is equivalent to omega n root 1 minus zeta square tp is equivalent to n pi, where n is represented as 1 to n, means 1, 2, 3 and so n. So the value for peak time to first overshoot is putting n is equals to 1. So the value is obtained as Tp is equals to pi by omega n root 1 minus zeta square. And the first minimum, that is undershoot, occurs at n is equals to 2. So T minimum is equals to 2 pi by omega n root 1 minus zeta square. So next, maximum overshoot. Generally, the maximum overshoot is represented by capital M P. The maximum positive deviation of the output with respect to its desired value is always known as maximum overshoot. So we rewrite the second order time response, that is C of t is equals to 1 minus e raised to power minus zeta omega n t by root 1 minus zeta square sin brackets omega n root 1 minus zeta square t plus 5. So the maximum overshoot occur at a peak time t equals to Tp. So Tp is pi by omega n root 1 minus zeta square. So after solving this, we put the value of Tp, that is the peak time, in this equation. So after calculating this, some value factor is crossed and cut down by each other. So a new Ct is obtained as C of t is equivalent to 1 minus e raised to power minus zeta pi by root 1 minus zeta square upon root 1 minus zeta square sin pi plus 5. Now C of t is equivalent to, because sin pi plus 5 is equivalent to minus sin of phi, so C of t is equivalent to 1 plus e raised to power minus zeta pi upon root 1 minus zeta square upon root 1 minus zeta square sin phi. So put the sin phi is equivalent to root 1 minus zeta square. So C of t is rewrite as this, and the value of root 1 minus zeta square is crossed with root 1 minus zeta square. Now C of t is equivalent to 1 plus e raised to power minus zeta pi by root 1 minus zeta square. So the maximum overshoot is equivalent to C of t minus 1. So 1 is cancel out. So m of p is equivalent to e raised to power minus zeta pi upon root 1 minus zeta square. So the maximum overshoot is obtained as e raised to power minus pi zeta upon root 1 minus zeta square into 100. So the maximum positive deviation of the output with respect to desired value is obtained as maximum overshoot. Next, settling time. So generally the settling time is defined as the time required for the transient response to reach and stay within the prescribed percentage error. So generally it is the useful design parameter which is defined as the time taken for the output to reach and remain within a zero of tolerance band of its final value. So generally the settling time for a second order control system is approximated as 4 times the time constant of this system for 2% of tolerance band. So Ts of settling time is equals to 4.1 upon del omega n, and that is the settling time for 2% band, and the settling time for 5% band is equals to T of S equivalent to T 3.1 upon del omega n. So these are the value for 2% band and 5% band. This is the value for 2% band. And note down for 5% band, 4 is replaced by 3. Means the formula is 3 by del omega n. Now steady state error. It is the difference between actual output and desired output. So steady state error is equivalent to limit t tends to infinity r of t minus c of t. This is the steady state error. Now we taken an example, that is the open loop transfer function of a servo system with unity feedback is given by, that is g of s is equivalent to 10 upon s plus 2 s plus 5. So determine the damping ratio, undamped natural frequency of oscillation, and what is the percentage overshoot of the response to a unit step input. So g of s is equivalent to 10 by s plus 2 s plus 5. Here h of s is not given, so we taken h of s feedback system is equivalent to 1. We know that the characteristic equation is 1 plus g of s, h of s is equivalent to 0. So put the value of g of s and h of s in this equation and solve this. So after putting the value, we obtain an equation, that is a characteristic equation, that is s square plus 7s plus 20 is equivalent to 0. Now this equation is compared with the second order system characteristic equation. So after comparing them, omega n square is equivalent to 20, that is this. 2 del omega n means 2 zeta omega n is equivalent to 7, and so because of this we find the omega n. So omega n is equivalent to root 20, that is 4.472 radian per second. Now 2 del omega n, put the value of omega n here. So we obtain 2 del omega n is equivalent to 7. Here zeta is also rewrite as del. So zeta is equivalent to 0.7826. Now for maximum overshoot, we know that maximum overshoot is equivalent to e raised to power minus zeta pi upon root 1 minus zeta square. So put the value of zeta in this equation. So we find the maximum overshoot is equivalent to 1 minus 92%. Next, second question, a feedback system is described by the following transfer function, that is g of s is equivalent to 12 by s square plus 4s plus 16, and h of s is equivalent to ks. So the damping factor of the system is 0.8. Determine the overshoot of the system and value of k. So we know that c of rs is equals to g of s upon 1 plus gs hs. So put the value of this here. So we obtain the characteristic equation, that is s square plus 4 plus 16k s plus 16 is equivalent to 0. This is the characteristic equation. Now compare with second order characteristic equation. So we obtain omega n square 16, 2 del omega n is 2 zeta omega n is equivalent to 4 plus 16k. So put the value of 2 zeta and omega n. So we obtain this. So because of this we obtain k is equivalent to 0.15 here, and omega n is equivalent to 4 radian per second. So the maximum overshoot, put the value of zeta in this equation. So the maximum overshoot is obtained as 1.5%. Now this is the example of the order functions. So thank you.